All right, so today we're going to dig into this paper on shower deconstruction. Sounds kind of intense, right? But from what we've gathered, you're ready to really get into the nitty-gritty of how scientists search for new particles, kind of like how they found the Higgs boson a while back.
Yeah, absolutely. It's a fascinating challenge. We're talking about trying to analyze these incredibly chaotic events where you have billions of these particle collisions happening every second at the Large Hadron Collider.
Yeah, it's mind-boggling to even try and imagine. So this paper you sent, it's all about this new tool, shower deconstruction. Yeah.
Exactly. Imagine trying to spot like a single unique snowflake in the middle of a blizzard. That's sort of the challenge physicists are facing. And shower deconstruction is this really clever algorithm that's like using a microscope to zoom in on the aftermath of these particle collisions, looking for clues hidden within all the chaos.
So instead of homing in on one specific particle, they're analyzing these bigger picture patterns within the particle showers.
Yeah.
Okay, I'm hooked. Break it down for me. How does it actually work?
So it all starts with these particle sprays or jets that happen after a collision. Now, shower deconstruction goes a step further and analyzes the patterns of even smaller sprays within those jets, what they call microjets. And instead of looking for a specific particle signature, it calculates the probability of a particular microjet pattern coming from known physics versus something new, something undiscovered.
So it's kind of like how a fingerprint expert can identify someone even if they're in disguise. It's about the overall pattern, not just one specific detail.
That's a fantastic analogy. It really is like comparing those microjet patterns to a database of known fingerprints to see if there's a match, or if it's something totally new and unseen before.
That's incredibly clever. But how do you even start to calculate the probability of these events, especially since they're happening in a fraction of a second?
That's where the real ingenuity of this approach comes in. To even make these calculations possible, they created what they call a simplified shower. It's a model of particle interactions that, while less detailed than some full-blown simulations, still captures the essence of how particles split and transform. You can think of it like using a simplified map to navigate a city. You get all the major avenues without every little side street.
Ah, so it was finding that sweet spot between accuracy and actually being able to process all this data in a reasonable time frame.
Precisely. And one of the most interesting aspects of this simplified shower model is how it incorporates something called color connections.
Hold on, color. Now you've got me curious. We're not talking about the rainbow of colors I see in a box of crayons, right?
Not quite. It's a bit more abstract than that. See, in the quantum world, color actually describes how quarks and gluons, the particles that make up protons and neutrons, interact through what we call the strong force. It's a fundamental property they possess, kind of like an invisible charge.
Okay, so if it's not actual color, then what makes it a helpful concept for understanding these particle interactions?
Well, just like electric charge dictates how particles interact through the electromagnetic force, this color charge determines how quarks and gluons interact through the strong force. And this model uses the principle of color confinement to predict the likely paths of these particles.
All right, you're going to have to elaborate on that one. Color confinement. It sounds like something out of a sci-fi movie.
It might sound strange, but it's actually a pretty fundamental concept. Basically, quarks and gluons are never found by themselves. They're always bound together in composite particles. So this simplified shower model uses that principle, that idea of color confinement, to predict the likely paths of particles as they travel through the detector. Like, for example, when a gluon, which carries this color charge, splits, it has to produce two particles that together neutralize its color charge. The model uses this information along with the particle's momenta to predict the angles at which they'll fly apart.
So this color connection, it's kind of like an invisible string, or maybe a set of rules that dictates how these particles are going to behave.
That's a great way to visualize it. And that leads us to another really crucial part of their model, these Sudikoff factors. Now, these factors account for something that might seem a little counterintuitive at first.
Oh, I do love a good counterintuitive concept. Lay it on me.
So Sudikoff factors deal with the probability that a particle didn't split at a higher energy level, which sounds odd, but it's really important for making accurate predictions. Imagine you're looking at a tree and you can see all its branches.
Okay, I can picture that. Lots of branches, some big, some small.
Right. Now, the Sudikoff factor is like taking into account not just those branches that you see, but also the spaces between the branches where new branches could have grown but didn't.
So to understand how the tree grew, you have to look not just at where branches are, but also where they could have been. That's fascinating.
Exactly. Every particle has a certain probability of splitting into other particles as it travels through the detector. And these Sudakov factors take into account the probability that a particle didn't split at each stage, which ultimately influences the final microjet patterns that we observe.
I'm starting to see how unbelievably complex this all gets. It's like this whole other level of detective work. We've got these simplified showers, the invisible strings of color connections, and then factoring in all the what-ifs with those Sudakov factors. It's all about trying to reconstruct the most likely story of what happened in that split-second collision to see if it points to something completely new.
You've got it.
Right.
And to demonstrate just how powerful this technique can be, the researchers decided to apply it to a particularly tricky challenge, identifying the signature of a Higgs boson decaying in a very specific way. So this is where things get really interesting. The researchers, they decided to focus on a specific type of Higgs boson decay, the one where it transforms into a bottom quark and an anti-bottom quark. And this type of decay, it's notoriously difficult to detect, let me tell you.
Oh, really? What makes this particular decay so much harder to spot? It's like trying to find a specific grain of sand on the beach or something.
It's almost like trying to find that grain of sand while someone's building a sandcastle right on top of it. You see, you've got all this background noise from other processes that also produce bottom quarks, which makes the signal from the Higgs decay incredibly faint.
Okay, so how does shower deconstruction help cut through all that clutter? How do you separate that Higgs signal from everything else?
Well, remember those color connections we were talking about? The way quarks and gluons are linked by these color connections when a Higgs boson decays? It's actually distinct from other processes that also produce those bottom quarks. It's like the particles carry a hidden signature of where they came from.
So it's not just about the particles themselves, but these invisible color connections are like a trail leading back to the Higgs boson.
You got it. And shower deconstruction, it's really good at picking up on those subtle differences in the color flow, which lets researchers isolate that faint signal of a Higgs boson decay, even with all the noise.
Wow, that's remarkable. So it's like this method can actually see these invisible strings connecting the particles, decipher their history, and tell us were they woven together by a Higgs boson or by something else entirely. But even with a tool this powerful, you still have to account for uncertainty, right? I mean, how do you make sure your model is giving you good information?
That's a really important point, and it's why the researchers in this case actually went a step further. They used two different event generators, Pythia and Herwig, to simulate these particle collisions.
Wait, two different simulators. Why not just use one? Seems like twice the work.
Well, it's all about getting a more well-rounded perspective. Think of it like getting a second opinion from a different expert. While both of them are powerful tools, Pythia and Herwig use slightly different assumptions, different algorithms even, to simulate these particle showers.
So by comparing the results from both simulators, you can get a better sense of how those underlying assumptions might be affecting the outcome.
Exactly. It helps expose any potential biases and just gives you a more accurate picture of the underlying physics at play.
That makes a lot of sense, like cross-checking your work to make sure you didn't miss something crucial.
Mm.
Did they find any interesting discrepancies between what Pythia and Herwig predicted?
Actually, yeah, there were some subtle variations, which I think just highlights that even in a field as precise as particle physics, there are always multiple perspectives to consider. It really drives home the point that science is always a work in progress, always striving for a more complete understanding.
Right, a good reminder that there's always more to learn, and that even our best models are still just, I don't know, approximations of something much more complex. But getting back to the results, how did shower deconstruction do overall? Did they manage to actually pin down those Higgs boson decays?
The results were really promising. They found that shower deconstruction could effectively separate that Higgs boson signal from all the background noise. In fact, it actually outperformed another technique that's commonly used for this type of analysis.
Wow, that's huge. It sounds like shower deconstruction has the potential to really change how we search for new particles, maybe even uncover some big secrets the universe is hiding. But like any scientific discovery, I'm sure there are some caveats, right?
Of course. It's important to remember that even with this increased accuracy, we're still dealing with probabilities, not certainties.
Meaning there's always a chance, however small, that the model could be wrong or that we might misinterpret the data.
Exactly. And that actually leads us to a really fascinating question.
Shower deconstruction relies on probabilities, and that means there's always room for the unexpected, right? Could there be particles out there or even interactions that just completely dip our current models? something that might throw a wrench into the works and mess with how we interpret the data?
That is such a good question, and it really gets to the core of scientific exploration, because it's totally possible that there are particles out there we haven't even dreamed up yet, forces we don't know about, interactions that our current models just completely miss.
So even with something as powerful as shower deconstruction, we're still limited by, well, what we think we know about the universe,
Right.
right? We could be totally missing something revolutionary.
It really puts things in perspective, doesn't it? Think about how we discovered dark matter. Astronomers were observing these gravitational effects that just didn't make sense based on the matter we could actually see. And that led to this idea that there's this invisible stuff, this dark matter, that makes up a huge chunk of the universe.
And we can't even see dark matter directly. We just know it's there because of how it interacts with stuff we can observe. It's like trying to solve a puzzle, but some of the pieces are invisible, but they still affect how everything else fits together.
What a great analogy. And it's possible that there are similar clues hidden within the data from the Large Hadron Collider, hints of something beyond our current understanding, something that doesn't quite fit into those neat categories our models provide.
It's kind of exhilarating and a little intimidating at the same time, wouldn't you say? On one hand, we could be on the verge of some major discoveries, things that rewrite physics textbooks. But at the same time, we have to be open to the possibility that the tools we have, they might not be enough to wrap our heads around these new frontiers.
That's the beauty of science, though, right? It's this constant journey of exploration, pushing those boundaries, always questioning what we think we know. And yeah, shower deconstruction is a major step forward, but it's not the end of the road by any means. It's like we've been handed this incredibly powerful telescope, letting us see farther and more clearly into the cosmos.
And who knows what incredible wonders are waiting for us out there. New particles, new forces, maybe even entire dimensions that are completely beyond anything we can even imagine right now. It's enough to make your head spin.
It certainly is. But that sense of wonder, that drive to untangle the mysteries of the universe, that's what keeps pushing scientific discovery forward. And with tools like shower deconstruction at our disposal, who knows what groundbreaking discoveries are just over the horizon.
Well, I can't wait to find out. Thanks for joining us on this deep dive into the amazing world of particle physics. It just goes to show, even in a field known for its precision, there's always more to discover. And until next time, keep those questions coming because the search for new knowledge never ends.